Welcome back. This is section 6.2, trigonometry of right triangles. So in this section, we're going to look at 6 different trigonometric ratios that we can actually use to help us find side links and missing angles as we progress through the rest of this unit and then even through the rest of the course. So the first thing we're going to look at are those 6 ratios that I just mentioned. The top 3 are going to be the most important for us because if you can memorize the top 3, then the bottom 3, if you notice, are just reciprocals of those top 3. So see that sine is opposite over hypotenuse, and then cosecant below it is just hypotenuse over opposite. And the same is true for cosine and secant, for tangent and cotangent. And so I'll write out the actual names of each of these because we abbreviate them with 3 letters. But the first one here is actually read as sine. The second one here is read as cosine. And our third one here is tangent. Right? And then the 3 reciprocal identities are going to be read as cosecant, secant, and cotangent. And again, we use those 3-letter abbreviations for each one anytime we write them out. Okay, but when we pronounce them, we read them that way. Now, one way that I have learned to remember these is by a mnemonic. Some old hippie caught another hippie tripping on acid. Okay, so I know that's not really PC, but that's one way that I've remembered this for all these years. I learned it back in high school. Okay, and so you can notice here we've got the letters S, O, and H. So our sine is going to be opposite over hypotenuse. Then we have cosine is adjacent over hypotenuse, C-A-H. And then the T-O-A gives us tangent is opposite over adjacent. And some people just remember it as SOHCAHTOA. Okay, so if that works for you also, that's fine. Or you can use this mnemonic here to help you remember what those ratios are. And again, once you know those top 3, then all we have to do is take the reciprocals of those to get cosecant, secant, and cotangent. Okay, and you can see down here in our triangle, we're always basing it off of wherever the theta angle is located. So if theta is down in that lower left-hand corner, the opposite side is going to be across the triangle from that theta. The adjacent side is going to be next to that angle, and your hypotenuse is always the longest side of your right triangle. It's always across from the right angle. Okay, so if we were to switch where theta was located in this triangle, that would switch where the opposite and adjacent sides are. That hypotenuse would still stay in the same place though, because it's always across from the right angle. All right, so let's take a look at example 1. We want to find all 6 of those trig ratios for the angle theta that's given in this triangle. Okay, so I'm going to start with sine. So we'll say sine of theta. And so notice here, our theta is down in that lower left-hand corner, which means the opposite side is going to be the 2. The adjacent side is going to be the square root of 5. And our hypotenuse this time is going to be 3 because it's across from that 90-degree angle. So if you remember back to the last slide, sine is going to be opposite over hypotenuse. And so our opposite is 2. Our hypotenuse is 3. And so sine of theta is going to be equal to 2 over 3. Okay, and we'll do cosine. Again, cosine should be A over H, so adjacent over hypotenuse. And so when we do our adjacent side, that's going to be square root of 5. We're going to put that over the hypotenuse, which is 3. And then our tangent of theta is going to be the opposite over the adjacent side. The opposite side is 2 here. The adjacent side is square root of 5. And I'm perfectly fine with you leaving things with square roots in the denominator. Sometimes it is useful to what we call rationalize these. So I'm going to go through that process real quick. But in general, on a test, I'm okay with you leaving answers like this. If you wanted to rationalize, we multiply by the square root in the denominator on top and bottom. Okay, and so when I do that, that's going to give us 2 times the square root of 5 And then square root of 5 times square root of 5 is square root of 25, which is just 5. And now I've gotten rid of that square root in the denominator. And so again, I'm perfectly fine with 2 over square root of 5 as an answer. Sometimes, though, it is useful if you're trying to match things up to rationalize those answers. And then we know the other 3 trig ratios should just be the reciprocals of each of these. So it's just a matter of keeping in mind which ones associate with the others. So sine is going to go with cosecant. So I'll do cosecant next. And cosecant is just the reciprocal of sine. So that's going to be 3 over 2. And then we'll do our secant. Secant is just the reciprocal of cosine. So I'm going to flip that fraction. That gives us 3 over square root of 5. And again, I'm perfectly fine with you leaving that in the denominator like that. If you want to rationalize, just multiply by square root of 5 on top and bottom. And then finally, cotangent of theta is the reciprocal of tangent. And so that should give us square root of 5 over 2. So the key here is just to make sure that you've labeled your sides correctly, identify where theta is, and then label the opposite, the adjacent, and the hypotenuse correctly. And then you should be able to find each of these 6 trig ratios. All right, so number 2 says if cosine of alpha, so this symbol right here is an alpha symbol, is equal to 3 over 4, we want to sketch a right triangle with an acute angle alpha and find the other 5 trig ratios of alpha. All right, so first thing we want to do is sketch that right triangle. I'm going to draw a right triangle. Right triangles have to have a right angle, so I'm going to put my right angle in there. Now I'm going to put alpha, and it really doesn't matter where you put your alpha because we're going to put the sides in the correct location based off of wherever we put alpha. I'm going to put alpha down here in this lower right-hand corner. Okay, now, what we're given this time is the cosine. And if you recall, cosine should give us the adjacent side over the hypotenuse. So I know cosine of alpha is equal to 3 over 4. So 3 should be my adjacent, and 4 should be my hypotenuse. So now the adjacent side should be that side along the bottom that's adjacent to alpha, so that's going to be 3. My hypotenuse is the longest side across from the right angle, that should be 4. And so now it's just a matter of finding that missing side so that we can find all of our other trig ratios. And if you recall, we can use Pythagorean theorem in a right triangle to help us find missing sides. Okay, Pythagorean theorem says that a squared plus b squared is equal to c squared, where a and b are the 2 legs of your triangle, and c is always going to be the hypotenuse, that longest side. So this time I'm going to do 3 squared plus b squared, where this side over here is b, is equal to 4 squared. Now 3 squared is 9. We're looking for b, and 4 squared should give us 16. So now to solve this, I'm just going to subtract 9 on both sides. That gives us b squared is equal to 7. And then to solve this, I'm going to take the square root of both sides. And so b is equal to the square root of 7. Okay, and you might recall back in Math 171, typically when we take the square root like that, we would get a plus or minus. Since we're dealing with the length of a side here, it has to be a positive value, and that's why I don't really need the negative square root of 7. Okay, so my b side over here is going to be equal to square root of 7. Okay, so now in my triangle, I'm going to go ahead and label all of my sides so that it's easy to find those ratios. We already said that 3 is the adjacent. We said that 4 is our hypotenuse, and that means that square root of 7 over here is going to be the opposite side from alpha. All right, so we've already got cosine, so let's go ahead and do sine next. So sine of alpha should be the opposite side over the hypotenuse. Opposite this time is square root of 7. Hypotenuse is 4, so square root of 7 over 4 is our sine value. And we've already got cosine, so I'll go to tangent next. Tangent of alpha should be the opposite over the adjacent. Opposite this time is square root of 7. Adjacent is 3, so tangent is square root of 7 over 3. Right. Now I'll go ahead and do cosecant. So cosecant of alpha. Remember, cosecant is the reciprocal of sine. And so I'm going to take the sine value, I'm going to flip it, and that's going to give us 4 over square root of 7. And again, I'm fine leaving it just like that. Secant is next. So secant should be the reciprocal of cosine. So that's just going to give us 4 over 3. And then finally, we need cotangent. So cotangent of alpha should be the reciprocal of tangent, or just 3 over square root of 7. Okay, so anytime they give you one of your trig ratios and they tell you it's a right triangle, draw your right triangle, think about which two sides you have from that trig ratio, in this case adjacent and hypotenuse. We can use Pythagorean theorem to find any missing sides, and once we have all three sides, then we can find all of our trig ratios. All right, now some special angles that we're going to see a lot throughout the rest of this course and that you're going to want to start memorizing. 0 degrees, very common angle that we're going to see. 30 degrees, 45 degrees, and 60 degrees are probably the most common ones that we're going to use. And then our 90-degree angle is also pretty common. So if you're looking at, let's say, a 30-degree angle, and you want to know the sine of 30 degrees. So I'm going to use my table here. There's 30 degrees. I'm looking at sine. And so the sine of 30 degrees is going to be equal to 1/2. And that will always be true no matter how large or how small the triangle is. If you have a 30-degree angle and you're looking at the sine of 30 degrees, it's always going to be equal to 1/2. And then I could say, well, let's find the tangent of 60 degrees, right? So tangent of 60, I'm going to follow that down, and that should always be equal to square root of 3. So these are just some of the common ratios that you're going to see a lot. And the best way right now for us to remember these is to look at these two triangles over here, because anytime you have a 30, 60, 90 triangle, like this one down here in the lower right, the ratio of the sides is always going to follow this pattern. So across from the 30-degree angle, that side length we can think of as 1. Across from the 60-degree angle, that side length is always going to be square root of 3 times whatever that shortest side is, which is 1 in this case. So just 1 square root of 3. And then our longest side is always going to be a multiple of 2 of the shortest side. And so in this case, 1 times 2 just gives us 2. So again, you can make this triangle as large or as small as you want, but the ratios themselves are always going to follow this pattern. Now, in a 45, 45, 90 triangle, like the one in the upper left, the side lengths are always, the legs are always going to be exactly the same length, right? Because it's an isosceles triangle, so in this case, 1 and 1. And if those two side lengths are 1, then the hypotenuse has to be square root of 2. And again, it doesn't matter how large you make this triangle, the ratios themselves are going to be exactly the same no matter how big you make it. Okay, so again, I would say start to memorize this table, okay, because these specific ratios for specifically 30, 60, and 45 degrees, you're going to really want to know because we're going to use them throughout the course, and you're going to just need to have them memorized. All right, now using a calculator. So if you've looked at your graphing calculator or scientific calculator, whatever you happen to be using to calculate these trig ratios, there is no button for cosecant, secant, or cotangent. The only 3 buttons we have are sine, cosine, and tangent. But we know that cosecant, secant, and cotangent are just the reciprocals of those other 3. So when we're putting things in the calculator that deal with cosecant, secant, and cotangent, we're just going to need to do 1 over the sine to get cosecant, 1 over the cosine to get secant, or 1 over the tangent to get cotangent. So even though there's not a specific button for those 3, we can still use our calculator to find them because they are just reciprocals of the other 3 that we have buttons for. All right, so let's try some of these out now. So first things first, we need to make sure that our calculator is in the correct mode. By default, most of the time, your calculator is going to be in radian mode. And so since we're dealing with degrees on these particular problems, we want to make sure we put it in the correct mode. So if you're on a TI graphing calculator, you're going to go to your mode. And then you're going to find where it says radians and degrees, and we want to make sure we switch that over to degrees and press enter. All right, now once you're in degree mode, now we can actually calculate the tangent of 40 degrees. So we're just going to put tangent of 40 into our calculator. And if we do that, I'm just going to round this to 4 decimal places. This should be approximately 0.8391. And in general, 4 decimal places is pretty sufficient for most of these types of calculations. Sometimes you might want to keep a few more if you're trying to get a more accurate answer, but for the most part, 4 decimal places is good. Right, now the next one, again, we have a cosine key, so we can just put cosine of 20 into our calculator. Again, we're going to have to round this because it's not an exact value. This should give us 0.9397. All right, now the next one, cotangent, we do not have a cotangent key, so we are going to have to use our reciprocals here. So we know cotangent is the reciprocal of tangent, so we're going to do 1 over the tangent of 14 degrees this time. So in your calculator, just do 1 divided by tangent of 14, and if we do that, we should get 4.0108. Right, and then our last one here, cosecant of 80 degrees. Again, there is no cosecant key, but cosecant should be the reciprocal of sine. So I'm going to rewrite this as 1 over the sine of 80 degrees. Sorry, I should have used an approximation symbol up here since we had to round that answer. So just notice anytime I use those squiggly lines, that just means it's an approximation. It's not an exact value. We have rounded something. That's why I'm using that symbol. Okay, but if we do 1 over sine of 80 degrees, that should give us 1.0154. So any of our 6 trig ratios now, we should be able to calculate for any angle using our calculator. You just have to remember with those other 3 that we do have to use reciprocals, so it's always going to be 1 over the 3 that we have a key for. All right, number 4, we want to solve the triangle ABC shown. Now, anytime it asks you to solve a triangle, it's asking you to actually find all the missing angles, all the missing sides. Okay, and it really does not matter what order you find them in, as long as you find everything that's missing. Now, looking at this triangle, I know that I have a 90-degree angle, right, because it's a right triangle, so we know this one's 90 degrees. We have a 30-degree angle, and one thing we know about triangles in general is that all the angles have to add up to 180 degrees. So I know that angle B plus 30 degrees plus 90 degrees has to equal 180. So I'm going to go ahead and find angle B because I know I can find that based off the information that's given. Well, 30 plus 90 should give us 120. And now if I subtract 120 from both sides, angle B should be equal to 60 degrees. And so I've found angle B now is a 60-degree angle. And you might have recognized this initially as just a 30, 60, 90 triangle. And if that's the case, you don't have to necessarily do all that work. All right, now, once we have all of our angles, now we can actually use our trig ratios to help us find the missing sides. Now, it really does not matter which of our angles we use. You can use either one you want. I'm going to go with the 30-degree angle since that's the one that was given. And so I'm going to start here with saying that A is the opposite and B is the adjacent. And then our 12 up here is the hypotenuse. So if I'm looking for side A, I know that from 30 degrees, I'm dealing with the opposite side and I'm given the hypotenuse. Since we're dealing with opposite and hypotenuse, that tells me I'm going to use sine. So I'm going to do the sine of 30 degrees is equal to my opposite side, which is A, over the hypotenuse, which is 12. Now we can just multiply both sides by 12 to get 12 times the sine of 30 degrees is equal to A. Now, if you recall, 30 degrees is one of those special angles from our chart. So I'm going to go back to the chart and I'm going to find the sine of 30 degrees, and that should give us 1/2. So this is 12 times 1/2 is equal to A. And 12 times 1/2 should just give us 6. So my side A should be equal to 6 now. Now, once you have two of the sides of your right triangle, you have some options. We could use Pythagorean theorem to help us find side B. That's one option. We could also use another trig ratio. And since we're dealing with these trig ratios and that's new, that's what I'm going to do here. But again, using Pythagorean theorem would be a perfectly acceptable way to find side B at this point. Okay. Now, if I'm looking for side B, and again, I'm dealing with this 30-degree angle, I know side B is the adjacent. Again, I was given the hypotenuse, so I'm going to use cosine this time. So cosine of 30 degrees is equal to B over 12, because that's our adjacent over hypotenuse. And then our steps for solving, very similar. We're going to multiply by 12. So 12 cosine of 30 degrees is equal to B. And again, 30 degrees is one of those special angles. So I'm going to go back to my chart. I'm going to find the cosine of 30 degrees, which is square root of 3 over 2. So we get 12 times square root of 3 over 2. And when we multiply that, 12 over 2 just gives us 6. I'm going to keep that square root of 3. So this is 6 times the square root of 3 is equal to B. So my B side is 6 square root of 3. Okay. And now if you look at the side links in this 30, 60, 90, you can see that they hold the same ratios as the one that was given in the chart, right? So even though the shortest side is 6, side B is just going to be 6 times the square root of 3. And then the hypotenuse is always twice as long as whatever the shortest side is, and 6 times 2 will give us 12 in this case. Okay, so they still hold the same ratio, even though it's a larger triangle than the one that was given with the chart. And once you found all the missing angles, all the missing sides, we have solved the triangle and we're done. All right, now angles of elevation and depression. Whenever you're measuring an angle of elevation or an angle of depression, you're always measuring from horizontal. So think like the horizon where the sun rises, right? Okay, that's going to be our horizontal line. So an angle of elevation is going to be measured from horizontal looking up at some object, right? So you can see the line of sight this time is above the horizontal, so we're going to have an angle of elevation. In the other case, if we have a horizontal line and we're looking down at some object, our line of sight is below the horizontal, we're going to have an angle of depression instead. But again, in both cases, we always have to measure from horizontal if we're dealing with angles of elevation or angles of depression. All right, so number 5, a giant redwood tree cast a shadow 532 feet long. We want to find the height of the tree if the angle of elevation of the sun is 25.7 degrees. So first thing I'm going to do, I'm going to try to draw ourselves a picture of what we're looking at. And I'm no artist, so don't laugh at my trees. Okay, but I'm going to have a tree. Okay, so there's my tree. Now, we know that the sun is going to be somewhere up in the sky and it's casting a shadow, right? So basically, the shadow itself is going to be along the ground. Okay, so I'm going to have my shadow somewhere along the ground, okay, that's cast by that tree. Now, the angle of elevation of the sun is going to be 25.7 degrees, which means if I'm standing at horizontal and I'm looking up at the sun, that angle is 25.7. So basically, if I were to take a point here on the tree and I were to draw a line straight down to the end of that shadow, that angle is going to be 25.7 degrees. So from horizontal, looking up towards the sun, that's our angle of elevation now. And we're going to assume here that the tree is upright, so it forms a 90-degree angle with the ground. And so basically we have a right triangle that looks like this. Now, the shadow itself, they tell us, is 532 feet long. And again, the shadow is along the ground, so that's going to be 532 feet. And what we're asked to find is the height of the tree. So I need to know how tall is the tree over here now. Now, based off the information that's given, we have an angle, we have an adjacent side, and we're looking for the opposite side. So notice here, this height is going to be opposite from the 25.7 degrees. Well, since we're dealing with opposite and adjacent, looking at our trig ratios, that tells me I'm going to do tangent. So I have the tangent of 25.7 degrees has to be equal to h over 532. So it's always the sine, cosine, or tangent of your angle is equal to whatever the trig ratio tells you, in this case, opposite over adjacent. Now to solve this, I'm actually going to move that 532 to the other side by multiplying. So we get 532 tangent of 25.7 degrees equals h. And at this point, 25.7 degrees is not one of those special angles from our table. So we are going to need to use a calculator to find this. Again, make sure your calculator is in degree mode, but then we can just put 532 times tangent of 25.7. And if we do that, we should get about 256 feet. And the reason I'm rounding just to the nearest whole number here is because the shadow itself was given to the nearest whole number. If you wanted to keep one decimal place more like the angle itself, that's perfectly fine too. But just pay attention when you're working on the homework. Typically, it will tell you how many decimal places to round to. And if it doesn't tell you to round to so many decimal places, it does want an exact value. So just make sure you're keeping exact values if it does not tell you to round. All right, and our last example from this section, from a point on the ground 500 feet from the base of a building, an observer finds that the angle of elevation to the top of the building is 24 degrees. Angle of elevation to the top of a flagpole atop that building is 27 degrees. We need to find the height of the building and the length of the flagpole. So again, first thing I'm going to do here is try to sketch a picture of what we're looking at. So we know we have a building and we know we have a flagpole on top of that building. So I'm going to draw a building. And on top of that building, I have a flagpole. Now, in our picture, it says from a point on the ground 500 feet from the base of the building. So I'm going to go from the base of the building, the bottom, I'm going to go out 500 feet. It says the observer finds the angle of elevation to the top of the building is 24 degrees. So just from the top of the building to the point 500 feet away, that angle of elevation is 24 degrees. But the angle of elevation to the top of the flagpole that entire angle there is going to be 27 degrees. Now, what we're asked to find is the height of the building and the length of the flagpole. So let's start with the height of the building, because if you look here, we have this nice right triangle, we have an angle, we have an adjacent side, and since we're looking for the height of the building over here, we know that's going to be our opposite side. So like the last example, since we're dealing with opposite and adjacent, we're going to do tangent. So I'm going to do tangent of 24 is equal to h over 500. Again, to get h by itself, I'm going to multiply both sides by 500. And 24 is not a special angle, so we do need to go to our calculator. And if we do that, that should give us about 223 feet. All right, so we've answered the first part. We found the height of the building. Now, the other thing we need to find is the length of the flagpole. Okay, so in this case, we can't just find that directly, because all we know is that the angle of elevation all the way from the ground up to the top of the flagpole is 27 degrees. So when we use that 27-degree angle, we're actually finding all of this. We're finding the length of the flagpole plus the height of the building all together if we use 27 degrees. And you might be saying, well, couldn't we just subtract 27 minus 24, get a 3-degree angle and use that? Unfortunately, no, because that triangle above is not a right triangle anymore, and so we can't use our trig ratios. Okay, so we do have to do it this way. We have to find the entire height all together, and then once we have the height of the building and the total height, then we can find the height of just the flagpole by itself. Right, now again, it is an opposite and an adjacent, so we're going to do tangent. So we have tangent of 27 degrees is equal to the opposite side over the adjacent side, so x over 500. Again, we're going to multiply by 500. Tangent of 27. And then if we put that into our calculator, that by itself should just give us about 255 feet. Now again, that's not what we were asked to find. We were asked to find just the length of the flagpole. But because we have the combined now height of the building and length of the flagpole is 255 feet, we know just the height of the building is 223 feet. Now we can just subtract, and that should give us just the flagpole by itself. So the length of the flagpole should be 255 minus 223. And when we subtract that, that should give us 32 feet. So just the flagpole by itself should be 32 feet, and the height of the building should be 223 feet. And as always, if you have any questions as you're working on the homework, please let me know. I'm always here to help. Please come and see me during student hours, and I will see you next time.